Okay, let's look at question 2 of Forces tutorial. Okay, we have a spring A and spring B. Let me highlight some stuff first. A with a force constant of 6 Newton per meter. Spring B with a force constant of 3 Newton per meter. Okay, they are connected this way. So there's a tension force of 0.60 Newtons over here. Okay, this will mean that on this end here, this is also pulling with 0.6 Newtons. Okay, so this is the same tension. Okay, so when you connect springs in series, right, you basically share out each spring is subjected to the same tension. All right. Okay, calculate extension of spring A. So for this, you just need to use your F equals to Kx, right? So this is just so X A is equals to 0.60 divided by 6.0. So we get 0.10 meters. All right. And then for B, XB, this is 0.60 divided by 3.0. So I get 0.20 meters. Alright, so this is the total extension. Alright, then you have what's the force constant of a single spring that will give the same extension. Okay, so let's call this spring C. So let's call it spring C. Alright, spring C, I want the extension when my F equals to Kc multiplied by Xc. So this is a new K that I'm supposed to find. I want the same force of 0.60 newtons and then Kc, and then the extension should be 0.10 plus 0.20. Alright, so you can work out Kc. Okay, Kc is just 0.60 divided by 0.30. Alright, so I get 20. Did I check my math already? Yeah, correct. So it should be 2.0 Newton per meter. Alright. Yep. So this is it for question 3. Alright. So this is how you combine springs when you want to calculate the extension. Realize that now the extension is actually smaller than the other two, as in the spring constant is smaller than the other two spring constants. This is smaller than that of A and that of B. Right. Alright, let's move on to question 3 now. Okay, I have a light wire of length 1 meter subjected to a force of 1 Newton. So again, highlight some of the stuff. 1 meter, 1 meter long, 1 Newton force. Okay, and then it extends by a length of 1 times 10 negative 4 meters. So it's about 0.1 mm, right? So calculate the force constant of the wire. Okay, so don't get confused by this is the length and this is the extension. Don't get confused by these two, right? They're not the same. Oh, sorry. This is the length and this is the force and this is extension. Length and the force and the extension is not the same thing. Right? So to calculate force constant of the wire, you will just use red color lah. You use K equals to F over extension. Alright, so this one will give you 1 Newton, 1.0 divided by 1.0 times 10 power negative 4. Right, let me grab my calculator quickly. Right, 1 divided by 1e negative 4. Okay, so that's 10,000. Okay, so that's 1.0 times 10 power 4 Newton per meter. Okay, so to get an extension of 1 meter here, right? 1 meter here, I need to apply 10,000 newtons of force, which is quite massive. Okay, set the assumption in your calculation in part A. So for all calculations involving this formula here, right, you need to say that basically Hooke's law still apply. That means your extension is still proportional to your force, right? It's still within the Hooke's law range of your object. Okay, next I cut this into 2 equal parts. Calculate the new extension of one of the part when a force of 6 newtons is applied to one of them. Alright, so this one over here, right? Okay, for this over here, you need to first decide what is the new spring constant. Right, so if we look at this original cable, let's just draw it here. Let's say this is my original cable. Wait, marker pen. Okay, original cable is this length. So this is the original cable. So just now when you stretch it, right, whatever force you exert to it, right, okay, you have a certain amount of extension. This extension is shared. Alright, so let's say at first my extension here, this is my whole extension, right? This is, let's say, x, right? This extension here is half. and it's half. Okay, it's shared. So for every, that means if let's say you divide by 2, you also share the extension now. So that means, right, I will have to apply the same force if I go by this one over here, right? Right now, my new K, okay, let's call it K prime, right? K prime is if I still take the 1 Newton force above, but now I share the extension into half. So this will become 5.0 times 10 power negative 5. Okay, because the original extension of 1 times 10 negative 4 has to be shared in half. Okay, then if I work out my new spring constant, this will definitely be 2.0 times 10 power 4 Newton per meter. Alright, then you use this value, right? You go and apply it inside your new force here. So right now I'm supposed to find extension. So x equals to F over K prime. So now the new F is 6 newtons. So I have 6.0 divided by 2 times 10 power 4. Okay. And this one, so this will give you, let me see what's the value. Ooh. Okay, let me try the value again. Okay, so 6 divided by 2e4. 6 divided by 2e4. I get 3 times 10 power negative 4. Right? Okay, so this is a new extension. Alright? Okay, for the next question, I'll just go through part B. Part A, I think is quite straightforward. Drag and friction between solids are similar. So basically, they just oppose your motion lah, right? Different is that when you have drag, it's only when it's moving. Okay, friction will occur even when it's not moving. All right. Part B is a more interesting question. What direction will friction be acting on its back tires? Okay, so you have a bicycle here. If you look at the bike, right? The bike tires, right, actually work this way. You have when you pedal, you are turning the wheel in this direction here. So let's zoom in some more. Okay, so if I just concentrate on this portion here, let me just box it up for you. Let's say just concentrate on this portion here. All right, this portion, if I look at my tire itself, right, the tire is moving in this direction. This is the direction of the tire. Okay, so this is the movement of the tire. So let's call it velocity lah. All right. Okay, so if the tire is trying to push back against the road will exert a frictional force towards the right hand side. Okay, frictional force. So it's pushing, therefore it's pushing the bike forward in that sense. Okay, so you have to zoom into this portion here. Don't look at the entire tire, because if you look at the entire tire, you get confused. Should I look at this portion, or should I look at this portion? Where actually I've just focused on this portion here. All right. Okay, so what's interesting about this bike here is that, okay, this tire, the rear tire is a driving tire. You are pushing the tire directly. All right, but then your main concern here, right? Okay, the next thing is what happens to the left, to the front tire over here. Okay, how does it work? Okay, this front tire here, right? Okay, so this front tire is not connected to the gear of the bike. So this front tire, if let's say you just imagine this whole tire here as a block, just imagine it as a square like this, for example. Let's say you don't allow this one to turn. Okay, then this tire is trying to move forward. This is the velocity. Okay, that means here, over here, we just zoom in again. We do the same technique. We zoom into this portion here. All right, this portion, the wheel is just trying to move forward in this direction. This is the velocity as well, if I don't allow the tire to turn. Okay, so in this case, right, your frictional force is actually acting to the back. Okay, so if then now you allow the tire to turn, right, your tire will go in this direction because of the frictional force. All right, so this is something interesting about your tires. There's a difference between the driving wheel at the back and the driven wheel at the front. The direction of friction is actually in the opposite direction if you analyze it carefully. Right? Okay, so in what direction would drag be acting on the man and bicycle? Drag force will definitely just be this way lah. This is your drag force. Okay, be to the left. All right. Okay, so that's it for question 4. Let's jump straight to question 5. All right. Question 5, you have a stationary car of weight W, stationary car on the road sloping at 30 degrees to the horizontal. Okay, frictional force is 4,000 newtons acting up the road. What's the magnitude of the weight W? Right, so you have frictional force, and over here, I think just need to make it a little bit stronger here. So this is frictional force, okay, 4,000 is F. Okay, and you have the free body diagram drawn there for you already. Okay, maybe it would, I think it's clear enough, I think you can tell, right? Okay, so for this, right, again, we need to use the same technique of resolving it along the axis, along the slope. Okay, so we use our, I think I've done this many times, this is the perpendicular axis, this is the parallel axis, alright? So we know that the car is only likely to move along this axis here, the parallel axis. It's not going to move up and down, alright? So, I don't need to resolve my normal reaction force because it's already perpendicular to the slope and therefore parallel to this perpendicular axis. I don't need to resolve my friction because it's parallel to the slope and therefore parallel to this one. Okay, I need to resolve my weight. My weight is vertically downwards now. So I need to chop it up to give you my x and y. My perpendicular and parallel. So I just do it this way. So let's use a thicker arrow to draw. Okay, so let's just draw it here like this. This is my W perpendicular. And then over here, let's use blue color now. I have my W parallel. Okay, and then if I work out the angle, let's just try this. Okay, let me make it a bit smaller now. Okay, this angle here, this is 30. This angle here is 30 degrees. So I can write it out. W perpendicular is equals to W cosine 30. And then W parallel is equals to W sine 30. Alright? So I know that I don't know normal force, so I won't use normal force to find. But I will say, okay, along slope, okay, my F net is equals to W parallel minus away frictional force. And this will give me 0. Okay, so this will be W sine 30 minus 4,000 equals to 0. So W is equals to 4,000 over sine 30. And I'll get, just scroll down, find the answer one. Alright, I'll get 8,000 newtons. Okay, 8,000 newtons. Okay, so that's the weight of the car. Right, next I'm supposed to find the normal contact force N on the car due to the road. Okay, so now since we know this is 8,000 newtons, right, we can just make use of the perpendicular axis now. So perpendicular to slope. Okay, again we do F net. F net is equals to normal reaction force minus away W perpendicular equals to 0. So this is N minus 8,000 multiplied by cosine 30 to give you 0. So N is equals to 6,900 newtons approximately. Right? Yep. So we make use of, so the key idea here is to make use of the slope. Make use of the slope to find the correct angle. Right? So once you can do that, right, it's quite straightforward. Just need to make sure that you identify clearly this W parallel and W perpendicular. Okay, and then you work basically along this axis and this axis. Alright, so that's question 5. Let's go on. Okay, we are now moving to turning effect. Okay, I'm going to assume that you've already watched the lecture. So if you've not watched the lecture, you need to watch the lecture first. Alright. Okay, forces are applied to a uniform rod of mass 2.55 kg and a length of 8 meters shown in the diagram below. Calculate the moment of the rod about point A and point B. Okay, I just want to recap what I learned at secondary school. Secondary school, usually when you find moments, right, you always take the center point, or you take, you might have been trained to take somewhere along the rod or here. But actually, if this system is in balance, right, you pick any point, it doesn't matter. You can take pivot about any point, right? It will still give you the same. It will still give you net moment to be 0, right? So, and the trick to understand about picking your pivot, right, is to pick a point, to pick the pivot to be at a point where it can get rid of a force that you don't know. Alright, very important. Okay, we'll try more of that later lah. Okay, let's look at question 6 first. You are given a uniform rod of mass 2.55 kg, length 8 meter. Okay, because it's uniform, right? Okay, so your CG will be right in the center. Okay, aeroplane flying over first. Okay, so the CG is here. So let's just draw in the weight vector this way. Alright. Okay, and we can work out the weight vector later. So this is 2.55 times 9.81. Alright. So now we take moments about A. Alright, that means now I'm taking, I use blue color for this part. So I'm taking moments about here. Alright. When I take moments for here, right, I can immediately eliminate A. Because remember the definition for moment is the product of the force and the perpendicular distance from the line of action of the force to the pivot. Alright. So we only are left with the moment due to B and the moment due to weight and the moment due to the 60 newtons. Alright. So let's do this. Let's just switch to a smaller pen. Alright. So moment about A. So that means this will be torque due to B plus torque due to W, right? Sorry, not B. Torque due to W plus torque due to the 60 Newton force. Okay. Or this should be minus. Okay, I'm going to take clockwise as the positive side. So I should minus here because this one over here, this is a counterclockwise and this is clockwise. Alright. So let's just switch to minus for this one. Okay. Minus. Alright. Okay, so torque due to weight is quite straightforward. This is just equals to 2.55 times 9.81 times 4 meters. Okay, because it's half of the rod. Okay, then for this one here now, right, for the torque due to 60, we need to consider where our pivot is. Alright, so we can either find the component of the force that is perpendicular to that is perpendicular to the pivot, or we can find the length that is perpendicular. Okay, so what I mean is that you can either find this force here, right? You can take this component here of this force that will form a right angle with your pivot, or you can extend this line all the way down and then find this distance here. Alright, so for this, right, I will just want to find this one over here first. So let me just draw it out first. Okay, let's draw it here. So blue color for this one. So to find this component, okay, and this is basically equals to minus 60 times cosine 60. So this is the force, okay, multiplied by the distance of 8.0. Okay, if you do that, then you check the answer for this one, you should get about 140 Newton meters. 140 Newton meters. Which one is larger here, right? Let me check. If I remember correctly, this is a negative value. So this is the anti-clockwise movement. Okay. This one over here, I think you can tell because this is 60 cosine 60 and this is 2.55 times 9.81. So this side here has to be bigger than this side. So your net torque is a counterclockwise torque. Okay. For point B, if I take point B as a pivot, right, then I will eliminate. If I take point B as my pivot over here, I will eliminate the weight component, the moment due to the weight. So for point B, let's just write it aside. So point B, the net torque, summation of torque is equals to the torque due to 10 minus the torque due to, actually both, okay, if you look carefully now, I forgot something. Okay, so this is your pivot. This will give you a counterclockwise moment. This will also give you a counterclockwise moment. Okay, so both are counterclockwise. Right, so I'll just do an addition here. Plus 60. Alright. Then same thing, I'll find the component that is perpendicular. Okay, that is along this line here. Okay, so I'm making use of this rod. Because this one is already given to me, this is 4 meter and this is 4 meters, so it's straightforward. So over here, this 10 Newton force, I'm making use of this angle. I want to find this component. So this is 10 sine 50. So 10 sine 50 times 4 plus 60 cosine 60 times 4 also. Okay, then I'll get a total of 151 Newton meter, anti-clockwise as well. Alright. Okay, so this is it. Quite straightforward. Okay, let me see where should I stop. Okay, let's do one more question at least. Alright. Okay, question 7. Okay, I have a heavy uniform beam of length L supported by two vertical rods as shown. Okay, what's the ratio of T1 to T2 of these two tensions? Okay, so you have this is connected in a way such that it's not balanced in the sense that it's not the center. This is 2/3 length, this is 1/3 length. You have T1, T2. Okay, so this system is in equilibrium. Remember when it's equilibrium, right? You have two conditions. You have net force in all directions to be 0, and then you have net torque about any point to be 0. Okay, so first one here, if we're talking about translational equilibrium, we say that F net equals 0 in all directions. Okay, so for this, right, I can make use of this fact here. Because this is a uniform rod, I will have a weight component here. Okay, I'm just draw it right in the middle here like this. Weight. And then this is halfway point. This is obviously at L lah. L over 2 lah. L over 2. Alright. Okay, so with this, right, and looking at this first condition here, I can say that, I can make this point. I can say that total upward equals to downward. So this will be, okay, let's write it out lah. Okay, what happened to my okay, so let me check something. Pause it first. Yeah, so I can say total upward equals to total downward. So total upward consists of, okay, our sum forces, okay, never mind. Our sum forces in the y direction, will give you T1 plus T2 minus W equals to 0. Okay, because net force in the vertical axis is 0. Okay, so I can come up with a equation that might be useful for later. W equals to T1 plus T2, right? Okay, next we can look at torque. We can use this to find. Alright, so one way you can do, right, is to take either this, first take this point as a pivot and then take this point as a pivot. You can do it that way. Alright, but another way of doing is to use the weight as a pivot instead. That means you take this point here to become the pivot. Let me just mark it here for you. Okay, if I take this to be a pivot, right, let's see what we can do. Okay, let me squeeze it here. Okay, so let me write it down. Okay, if I taking CG as pivot, okay, I can do this. I can say that if you look at this now, if the pivot is here, this will give you, T1 will give you clockwise, T2 will give you counterclockwise. Okay, so we can sum up counterclockwise torque is equals to the sum of counterclockwise torque. Okay, clockwise torque is just T1. Okay, so the torque due to T1 is equals to the torque due to T2. Okay, or the moment, torque and moment is the same thing. Okay, T1, what is the torque? Okay, so this distance here is L over 2. Alright, so you have T1 multiplied by L over 2. Okay, and then this distance here, this one over here, this is is it L over 2? No, this is, wait, half minus, no, 2/3 minus half, so that is 1/6, right? Okay, L 1/6, right? Okay, I think so. T2 L over 6. Let me check again now. Sometimes the simple stuff will trip me out. 2/3 minus half. 2/3 minus 4/6 minus 3/6. Yeah, 1 over 6. Okay, so we got ratio of T1, T2. Then realize actually you just need to shift T1, T2 to one side lah. So T1 divided by T2 is equals to L6 divided by L2. So you get crap, I can't do this. Okay, 1/6 divided by half. 1/6 by half, so you get 1/3. Alright? Alright, 1/3 is right. Damn. My math is failing me now. 1/6 divided by half. Yeah, 1/3. So T1 and T2 is 1/3. Okay, don't leave your answer in the fraction. Go to 0.333. lah, will do. Let me check my answer. I haven't checked my answer for this one, so maybe it's wrong now. Is it 1/3? Yeah, 1/3. Okay, can. Yeah, so that will do as well. Alright. If you want to, you can also take moments about either T1 or T2, then make use of this fact here. Make use of these to combine. Okay, so that's the way lah. So actually you don't really need this also. If you think about it, you don't really need this lah. Okay, you can just straight away jump to here and do. Alright. Okay, let's see. Should I push for one more before we take a pause? Because I need to see where to cut my video. Okay. Let's see. Let's see how many questions I do. Okay, let's do one more. Then we pause the video. Okay. Alright. Okay, I have a traffic light that's held in equilibrium by two supporting cables, A and B. Okay, so you have these two cables here, A and B. So it's pushing upwards now. Alright, then you are given the weight of the traffic light. You are told that the mass of the cable is negligible, so don't care about the mass. Tensions are T1 and T2 respectively. So let me highlight some stuff for you. With black color is better. Red color is better. 350, T1 and T2. Okay, sketch a labeled vector diagram of the forces on the traffic light. Okay, so you are now taking this point here. Okay, you are basically taking this point to be the point of your vector diagram. Okay, so first thing first, I have my weight. Okay, so this is fine. So this is weight, label in full. Okay, then you have T2. T2 is this direction. Okay, let's just label it T2, and then this angle here is 50 degrees, and then T1 is over here. T1, and this is 30 degrees. That's it. Okay, these are all in forces. There are no other forces. Okay, this is equilibrium, so it means net force in all directions is 0. Net torque at any point is 0 as well. Okay, so first thing first, determine the ratio of T1 to T2. Okay, so that's part B1. Okay. Oh, sorry. You're supposed to draw a vector triangle. So, then you can't draw it this way. You have to go. Okay, let's try again. Draw the weight. Okay, then draw maybe T1 first. That's fine. T1, and this angle here is 30, and then T2. This angle here is 50. Alright, we need to draw to scale. Alright, determine ratio of T1 to T2. Okay, for T1 to T2, right? Now if you just consider forces in the y-axis, actually I prefer to use this to solve lah. Okay, you can see that the weight downwards, T1 has an upward component, T2 has an upward component. Okay, so I can say that summation of forces in the y-axis will be taking upwards as positive. So up is positive, right is positive lah. Okay, so T1y plus T2y minus W is equals to 0. Okay, do we have the ratio? 350, right? Okay, 350 newtons. Okay, so T1y plus T2y is equals to 350. Alright, then we can get the ratio in. Okay, we get the ratio in. Oh, actually, it's easier way lah. Sorry. My mistake. I should use x-axis. Let me just erase off this portion here. Okay, let me erase off this. Okay, we use x-axis. Okay, because x-axis, right, is easier because there are only two forces. Okay, there is your T1x and T2x. These two will cancel each other out. Okay, so x-axis will be T1x. I go add the minus sign because this is to the left, right? Plus T2x is equals to 0. So essentially it's T1 sine 30. T1 sine 30 is equals to T2 sine 50. Okay, so you're supposed to work out ratio of T1 to T2. So T1 over T2 is equals to sine 50 over sine 30. Alright, then you get 1.53. Alright, so it's a ratio. Okay, or you can use the triangle to solve. If you prefer use sine rule to solve for this one, that's also fine. There's no issue with that. Whichever way you prefer lah. Because if you use sine rule, then we're writing this angle here is T1 sine 50. Yeah, you can try and see your own lah. I don't really like to do sine rule, but whichever rocks your boat. Okay, that's fine also. Okay. Alright, then state, okay, I double the weight of the traffic light. If I double weight of traffic light, state any effect, if any, on ratio T1 to T2. Okay, your traffic light, right? When you double it, you will change the this will become bigger. Alright? So this two obviously has to become bigger here. But both of them also become bigger. Okay, but if you just go by the equation alone, right? Just look at x axis, right? You notice that this x axis, right? It has no impact on your weight. Okay, it does not involve your weight. So it doesn't involve your weight, right? Then the angle will stay constant. Okay, then basically what will happen here is that both values will grow at the same time. Okay, they're both increment because of the increase in weight. Okay, so there's no change in your ratio lah. Okay, because these two values are independent of your weight. Alright, as in the ratio of these two values are independent of your weight. Alright, so there's no change on the ratio when I double my weight. Alright. Okay, let's see. Shall we do one more? Might as well just. Okay, I think got one more question for tutorial 2 lah. Let's finish this once and for all. Okay, question 9. Question 9, right? I have a uniform metal beam that's pivoted at one end and held equilibrium in the horizontal plane by the cable attached to its own. Okay, so this is pivoted at one end, there's a pivot here, and then there's a tension here. Alright, then you have a weight, you have a bricks here, and then, okay, so let's see, find some stuff first, be more systematic, right? Okay, mass 210 kg, length 8 meters. Okay, cable makes angle of 32 degrees. Okay, so this 32. Okay, has a tension of T. Power bricks mass 150 kg is placed on the beam. Okay, you're asked to draw 3 other forces. Alright. So of course we have the tension there. There's only one given. So let's draw in the other forces. I'm going to use blue color here. First we have the weight of the beam. Okay. Next, it's tempted to say weight of the bricks, but it's not. This will be. Okay, let me draw it here first. Okay, normal contact force due to weight of bricks. Okay, please distinguish this between the weight of the bricks and the normal contact force. This one here, right, is a pushing force. This force here is a pushing force on the beam. Okay, this is a result of this force here is acting on the beam of the bridge. Remember, if you draw the bricks alone, right, it looks like this. Bricks alone, you have this weight, and then you have normal force from the beam. Okay, so this force here, and this force here, right, they are Newton third law pair. Alright, but since I'm supposed to draw a free body diagram of the beam, right, I don't draw in these two forces. I only just draw this one because this force and this force acts on the bricks, but this force here is the one acting on the beam. Alright, and there's one more force here to draw. There's also this contact force here. This contact force from the pivot, right? We don't know the direction yet, but we know for sure it has to be pointing outwards. Okay, how do I know for sure it's pointing out? Okay, let's look at the forces that we've drawn so far. We have this one here. We have the weight, normal contact force due to weight of bricks. We have the weight of the beam. We have tension. Okay, tension is the only one that has a horizontal component, and this horizontal component is this way. Okay, so for a system to stay balanced, right, the beam has to exert a rightward force. Alright, and also for now, we don't know for sure whether this beam will exert an upward component or downward component. It all depends on what's the relationship between these three forces here. Okay, so for now, I will just draw it upwards first. Usually, okay, no, I won't say usually upwards, but I'll just draw upwards first. Okay, and just label it. Okay, so this one, let's call this reaction force on beam due to hinge. Okay, so 3 forces here. Not reaction force on beam due to hinge. Okay, so explain what will happen to a tension T in the cable as the power bricks is moved towards NP of the bricks. Okay, so this one here, okay, let's look at this diagram now. If I take this point to be the pivot, if this is a pivot, right, then you see that, oh, actually, my normal force due to bricks, right, is exerting a clockwise moment. okay, and the weight of the beam is also exerting a clockwise moment. Okay, these two are balanced by your rod, which is giving you a anti-clockwise moment. All right. So right now the system is such that okay. So let's write it here. Okay, let's use blue color now. Okay. Oops, so fat. Taking hinge as pivot. Okay. Sum of clockwise moment equals to sum of counterclockwise moment. Okay. Counterclockwise moment is given by t. So that okay. Anyway, clockwise moment, right? You have torque due to normal contact force plus torque due to weight equals to the torque due to tension. Alright, this is the basic idea law. Alright, so if I shift to P, right? Okay, so if I shift this over to here, for example, right? If I shift it to here, right? I'm increasing the distance of, I'm increasing this distance here. Okay, so shift bricks to P. What will happen is that perpendicular distance of N, not the normal contact force to pivot increases. Okay, once that happens, right, the torque due to the normal contact force will increase. Okay, so then we go back to this first equation over here. If I increase this and this stays constant, right, this has to increase as well. Okay, but then when that means when this increases, right, okay, so the torque due to T increases because the distance of T to the pivot, right, cannot change. It's still this distance here. Okay, or if you want to resolve it, then it's this distance lah, it's fine. Okay, so because your distance cannot change, right, then as a result, right, your tension has to increase. Okay, so that's a rationale to why T will increase. All right. Then next, you are asked to calculate some stuff. Okay, Paul is moved a distance, place a distance of 5.3 meters away from P. Calculate the tension T in the cable. Okay, so let's try this one now. Okay, so we use the same calculation above. We use okay, let's write it out here. So torque due to normal contact force plus torque due to W equals to torque due to tension. All right. So the P is 5.3 meters away from P. This beam is how long? 8 meters long, right? So this is normal contact force. How much? This weight is 150. Okay, so 150 times 9.81 multiplied by 8 minus 5.3. Okay, then for the torque due to the weight, this will be torque due to weight of, okay, so this will be 210 times 9.81 times 4.0. Okay, and equals to tension. Okay, torque tension. Okay, so for this one here, I'm just going to resolve this one. I want to find this component here. So this is my, just draw it out, Ty. Okay, so this will be Ty. Ty will be expressed, okay, let's write it here first. So this is Ty multiplied by the distance of 8 meters, alright? So 8.0. Okay, then we solve for, then you know that Ty is equals to T sine 32. Okay, 32 degrees. Okay, so once I solve for Ty, right, then you can go and continue to solve for T lah. If you do this right, your answer should be about, let's see what the answer is, 2880 newtons. Okay, so T is equal to 2880 newtons. Alright. Okay, so that's for T. Okay, next you're supposed to determine the magnitude and direction of the force exerted by the pivot. So the hinge here lah, this point here. This point here. Alright. So for this, right, I can work out the net. Okay, I can take the pivot here lah, but then I realize this is an angle and I don't know the angle. If I know the angle, I can do, but I don't know the angle, so I can't do it that way. So I need to make use of the net upward force, the net vertical force, and the net horizontal force. Okay, so for this, let's write it out over here. Okay, so I do summation of forces in the x-axis. It will be right hand side positive. So it will be, let's call this force Let's call this force, I don't know, what should I call it? Let's call it force P lah, pivot, right? Okay, let's call this point P. Okay, so this is P. This is P lah, right? Okay, so this will be P px plus px minus tx should give you 0. These are the only two horizontal forces in the system, px and tx, right? So if you have this, you can work it out because you know this will be px. Okay, so px is equals to tx, right? So this will be 2880 cosine 32. All right, and then you get 2442 newtons. Okay, then for y-axis, okay, it's a bit more stuff. You remember we took py as upwards first, right? So we have py plus ty, which is also upwards, minus away the weight, which is downwards, minus away the normal contact force due to bricks, which is downwards as well. And this whole thing gives you 0. Okay, so you can write in the values now. This will be this is py is equals to n is 150, right? So 150 9.81 plus 210 9.81 minus ty 2880 sine 32. If you do this, you'll get 3160 newtons. Okay, so these are the two numbers that you want: 2442 newtons and 3160 newtons. Sorry. 2005 newtons. What I'm doing. I was looking at wrong numbers. Okay, hold on. Erase this one first. Okay, so this one will be 2005 newtons, right? Okay, so once you have this, you can draw a simple diagram. Both are positive values, right? So that means px is here, px is here, py is here. Okay, then you just need to find this angle here, p, and then this angle here. Okay, so to find p is just equals to px square plus py square root. And then to find the angle, theta, right? Theta is just tangent inverse of py over px. Okay, and then you should get 39.4 degrees. Okay, so this answer here, this is equals to 3160 newtons, and this angle here is 39.4 degrees, right? That's all for tutorial 2. We will come back to tutorial 3 very soon. Alright.